For this problem, we are given a peptide, a pentapeptide, CLASS, and we are asked to draw the complete chemical structure, probably at pH 7. Let's do at pH 7. Calculate the pI and determine the net charge at this pH 7 and indicate hydrophobic and hydrophilic amino acid residues. So the first letter stands for N-terminal amino acid and C stands for cysteine. So I'm going to draw it in the center of my page, starting with alpha amino group. Then I'm going to draw a alpha carbon, peptide bond, then alpha carbon of the next one, the second peptide bond, alpha carbon of the third amino acid, third peptide bond, alpha carbon of the fourth, and finally the last peptide bond. So the first amino acid is cysteine, that. Then I have L, it stands for leucine. It doesn't have an ionizable side chain. Then I have alanine, and then I have 2 serine amino acid residues. So here, the only ionizable side chains will be alpha amino group with the pKa of 8. For cysteine, for the side chain of cysteine, we have pKa of 8.4. And finally, we have alpha carboxyl group with the pKa in peptides 3.5. Serine doesn't have pKa, so a side chain that can be ionized in aqueous solution unless it's in the active sites of certain proteins where the microenvironment affects pKa, kind of decreases pKa to make it feasible to deprotonate that. But we don't account for the those situations here, so we treat serine as non-ionizable polar amino acid residue. So as you can see, at pH 7, we would have both cysteine side chain and alpha amino group protonated, meaning the side chain will be neutral. The alpha amino group will be protonated like that, exactly as we drew it, and that's because pKa of, let's say, alpha amino group is greater than 7, right? And the same is true for the pKa of cysteine side chain. As for the pKa for alpha carboxyl group, it is less than 3.5, less than 7. And because of that, we know that carboxyl group will be deprotonated and negatively charged, again as drawn. So pretty much the structure that we already drew will be exactly the structure that we want to draw at pH 7. And now we can determine the net charge for that peptide. So because here we have one positively charged group, one negatively charged group, and that's it, we know that the net charge at pH 7 is 0. And that's exactly the charge that we are looking for when we are determining pI. So pI will be the pH at which the amount of that neutral form that we drew is maximized. So this neutral form is present in its maximal possible concentration. And for that, we know we need to deprotonate this alpha carboxyl group as much as possible before we start deprotonating this group. So based on that, we are averaging actually the pKa's for alpha carboxyl group and alpha amino group. And that gives us the value 5.75, right? Close to 6. Now, in order for us to determine hydrophobic and hydrophilic amino acids, we need to kind of just analyze the structure of the side chain and recall that hydrophilic functional groups would like to be in water because they are forming either hydrogen bonds or dipole charge interactions with water molecules, and hydrophobic would not have such groups, such polar groups, so they will not like water. So let me highlight my hydrophilic groups using yellow highlighter. So I'll start with serine. It definitely has OH groups that would be polar. Neither alanine nor leucine doesn't have such groups, but cysteine is also considered a polar amino acid because it has that SH group that can be partially deprotonated even at pH 7, right? A tiny amount of it will be negatively charged. And also it can form rather weak but still hydrogen bonds and, of course, dipole interactions with water molecules. As for hydrophobic amino acids, the only two that I skipped while highlighting my hydrophilic groups are leucine and alanine. They have aliphatic alkyl radicals as functional groups, aliphatic side chains, and of course hydrocarbons or alkanes. They don't like water, so we can clearly say that those amino acid residues are hydrophobic.